Hi, and welcome to the Module 3 of Lecture 16, the last module in the last lecture of the last part of this course. And in it, we're going to be discussing implicit differentiation in multiple dimensions. Now recall, in the previous module, we discussed implicit differentiation in one dimension. And the problem went like this. Typically, you want to maximize some function. That maximization problem produces a first-order condition, such that the optimum of that first-order condition, x star, is itself a function of the parameter c. The parameters also are in there. And that first-order condition is set equal to 0. And this implicitly defines the optimum x star of c. Obviously, in case 3, we can explicitly set up x star and c like so it's just a function of c. You don't need to do anything anymore. You can just differentiate h of c with respect to c explicitly and be done. That's what we covered in the first module. But we're assuming here that you can't do that for whatever reason. We discussed some possible reasons in the previous module. So we can use if we can't explicitly define it, we can use the implicit function theorem to get this derivative here, the one we want, the rate of change of the optimum x star as a function of c, the parameter c. That's going to equal partial g partial c evaluated at x equals x star divided by partial g partial x evaluated at x star. Okay. And this works fine for one dimension and it's very helpful and useful. Oftentimes you have more than one dimension though. In some cases it's okay. So for instance, if you have more than one c, so c is a vector now, well, you can treat each ci independently. I'm writing it as a total derivative instead of a partial, even though it's kind of a partial. I'm assuming that all the c's are independent and therefore the total and the partial are the same thing. If you have a whole bunch of independent x's that are not related to each other at all, and one c, you could treat each one of these x's separately, again, assuming they're not related to each other. Sorry, this is not a vector. That's fine too, and again, these would be partials, but because they're not related, these are total derivatives. That's, by the way, this is pretty uncommon. This is not so uncommon. But sometimes you don't have these situations. When is that? Well, let's say I'm taking, I have more than one actor in some game, and I'm simultaneously maximizing their utilities. So I'll have, for instance, an F1 and an F2, and maximizing those would produce a G1 and a G2, and maybe more Gs, but let's stick with 2 for now for this example. And each one of these will be a function of x star. And there's an x1 star and x2 star, so x star is also a vector. And maybe there's more than parameter too, so the parameter is also a vector. So in essence, I have a vector g and a vector x and a vector c. Now, if these are linear, if these first order conditions are linear, we can use the techniques we talked about in the previous part of the class to go through and solve these system of linear equations. Typically, they have the same number of unknowns as equations, so you can typically often solve these things, not always, but often, because they're set up that way in these games. But sometimes you will not get a system of linear equations. And in those cases, sometimes you will not be able to actually solve the system to get what you want, which is, let's write in red so you can see it better, this in the very bottom. Right? You want x1 star equals some function of h, and x2 star equals some function of h, some different function. And the important thing here to note in that red writing down there is that neither x1 star nor x2 star actually depend anymore on the other variable. x1 star does not depend on x2 star, and vice versa. And the benefit of that is you can very clearly understand how changing c affects x. If I vary c, I will vary h1 and h2 separately, and those will independently vary x1 star and x2 star, and you don't have to worry about any interactions that are complex. But you can only do this if you can explicitly solve for x1 star and x2 star independent of each other, and because these equations, these first order conditions are often nonlinear, you can't always do that. So instead, what you get is something that looks like this, right? x1 star is going to end up being some complicated function of the c's, and also x2 star, that's not a vector, sorry. And x2 star is going to end up being some different complicated function of the parameters, and also x1 star. And that's not actually solved because you haven't written x1 star or x2 star explicitly. However, you have implicitly defined x1 and x2 star via this system of equations. Sorry for that jostle. And that's the key. We're going to have to simultaneously address the whole system. Why is that? Well, consider the actual effects. Let's say we had one C, right? And let's say C had some direct effect on x1, but also had a direct effect on x2. Well, that's fine. If they were separated, then you could figure out what the effect of C was on x1 just by considering that direct effect. But since that's not separated, x2 also affected x1 from this equation up here. Again, that would be fine. You could use a total derivative chain rule, right? You could have x1 be affected by both C and also C indirectly via x2. However, there are two equations here. And x2 is also affected by x1. So when x2 changes x1, so if C changes x1 and x2, then x2 also changes x1, x1 will also change x2, which in turn changes x1 again, and so on forever, and the chain never actually resolves. And that is, in a nutshell, the problem, right? You can't just reason through this chain of logic because it goes on forever. Now, there are some cases that you will see as you advance in game theory in which you can assume, for instance, x1 and x2 are strategic complements in each actor's utility function. So the more you do, the more I want to do. In those cases, for very specific assumptions on the utility functions, you can say that increasing C will increase x1 and x2 because we know they're strategic complements. This is a sort of a subset of supermodularity, of the notion of monotonic rheostatics, which we talked about a little bit earlier. And that's a great technique to use when you can actually make those assumptions substantively properly. So that's that. However, if you can't do that, you're left with this infinite regress of x1 affects x2, x2 affects x1, and so on forever. So what do you do with that? What you do with it is you treat the entire system of equations at the same time. Okay. And this you do by using the implicit function theorem in multiple dimensions. So you have a system of equations that looks like this. Here G is a vector. X star is the value of x that makes G equal to 0, and C is a vector as well. That equals a vector of zeros, and here's our system of first order equations. Now we want to simultaneously deal with an entire thing at once in order to figure out what the rate of change of x is with respect to C. Each component of x, each component of C. So how do we do that? Well, finally, after introducing it back a few lectures ago, we're going to use the Jacobian. Recall, if we have a vector-valued function, the Jacobian allows us to take derivatives of the vector-valued function and put them into a matrix. So, recall that the Jacobian was J. An element of the Jacobian, there's two, like it's a comma, not a J. The I-kth element was equal to the partial derivative of the ith component of the function with respect to the kth component of x. So this is a Jacobian, which will give you the derivative of the function, the vector-valued function. But note here, there's only one possible Jacobian you could have. You could also have this Jacobian. G-I-C-K, because C is also a vector. Or you could also have this Jacobian, because x is also a vector. You could have the Jacobian corresponding to dx star, ith component of that, by partial xi star, effective ck. So you actually have three possible Jacobians. We will call this one Jacobian jx, this Jacobian jc, and this Jacobian jx star of c. Put commas here. And here are three Jacobians. So there's going to be a lot of algebra involved in computing, a lot of calculus potentially in computing all these Jacobians, but you can do it in theory. Now, once you do that, what do you do with it? You plug it into a very similar analog to the implicit function theorem in one dimension, which I'm not going to derive, but here it is. The Jacobian related to x star c, which remember tells you the rate of change of x star, the vector valued function x star. These are all vectors. I should probably stick little vector signs there. With respect to all the different components of the parameter c, it's going to be equal to negative j sub x vector inverse j sub c. And that is it. Note the analog to one dimension. There's a negative sign out front, first of all. The left-hand side is the rate of change of the implicitly defined function with respect to the parameters. It's effectively 1 over the derivative of the first order condition g with respect to the x's. Here it's 1 over it's an inverse matrix instead of just 1 over the derivative. But again, you need this thing to be non-singular. So this must be non-singular. Otherwise, you cannot invert it. That's an analog to the derivative not being 0 in one dimension. And then it's multiplied by the derivative of the function of g with respect to the parameters on top. So it's the same analog, but it has a more complicated form. But you can write it actually just as simply as before, as long as you remember what Jacobian is. And there you go. And note that the determinant of the Jacobian will come in when you compute the inverse of the Jacobian, which is why we discussed determinants of Jacobians before, because if the determinant of the Jacobian is not of this Jacobian j sub x is not non-zero. So if the determinant of the Jacobian jx is equal to 0, you can't invert it and you don't get an inverse function. So oftentimes you talk about the determinant of the Jacobian, as we discussed back a couple lectures ago. Okay, so that's all the theory. Again, we're not going to discuss existence or anything more complicated. That's complicated enough. And this is how you use the implicit function theorem in more than one dimension. We would conclude this module with a single example of this that's basically a simplified version of the one in the book. Okay, there as here, the example goes like this. You have, say, two warring groups who are engaging in conflict, and they can try to mobilize their individual troops, their individual populations, by providing particularized benefits. However, doing that takes away from the rents they can secure themselves later, so it's costly. The more they mobilize, the more the better chance they have of winning. So in the book, we use the general functional form of the chance of winning pi, requiring you to use the Jacobian. Here we're going to use specific functional form. So we could actually solve this thing explicitly, but we're not going to. We're just going to use it as an example of the Jacobian in more than one dimension. An implicit function theorem in more than one dimension. Okay, so here's the utility. So player 1's utility is going to be 1/2 plus b1, minus b2. So that means your chance of winning the conflict, which you called pi in the book, is 1/2 plus b1 minus b2. So if you have the equal contributions, your chance of winning is 1/2. And then minus c1 b1 squared, so that's the cost of contributing. Player 2's probability of winning is 1 minus this, 1 minus the first thing, so it's 1/2 plus b2 minus b1, and then minus c2 b2 squared. So C is a vector, C1 and C2 components. B is the vector, B1 and B2 components. And also the G's are going to be vectors, G1 and G2. So let's find G's first of all. G1 is the first order condition, which equals 1 minus 2C1 B1. And G2 is going to equal 1 minus 2C2 B2. And here again, you could solve these directly pretty easily. We're just going to go through this, see the example, see how it works, without knowing we could do that. It'll make life easier because we have a limited screen size to go through a bunch of algebra. Okay, so here's our functions. We know that at these functions, these things equal 0. We're not going to solve for them directly for a reason. We're very, very lazy, I guess. I'm going to go through and see how to apply the implicit function theorem in more than one dimension, which again was this. X inverse JC. Okay. So let's calculate a bunch of Jacobians. So let's calculate, well, two really. Let's do JC first. Well, JC, remember JC is, I'll do it up here because it's small. I have very little room to work here. JC is going to be the matrix. The first row consists of derivatives of G1 with respect to C1 and C2. That's negative 2. Negative 2B1 over here. And 0, because there's no B2, there's no C2 in there. And then over here, it's 0 and negative 2B2. If we can read that. There's the Jacobian for C. It's relatively straightforward because C's only appear multiplying the B's at the end. What about the more complicated JX? Well, because of the explicit form we use here, it's not so bad. JX is going to be this matrix. So you have the first row is the derivative of G1 with respect to B1, which is negative 2C1. There's no derivative of B with respect to B2 over here, so that's 0. And you have 0 and negative 2C2. So it's a nice easy form as compared to the other case that's a messier and less pleasant form. Okay. The good news is we can actually do this pretty simply and take the inverse without having to do much effort because it's a diagonal matrix. So the inverse of this thing is going to equal 1 over negative 1 over 2C1 and negative 1 over 2C2. If you don't believe me, you can go through and actually compute the inverse. It's a 2 by 2 matrix. The determinant is 1 over 4C1, C2. And so it's so the inverse is 1 of the determinant times you flip the order of the diagonals, so it's negative 2C1, sorry, 2C2, negative 2C1. When you divide through by 4C1, C2, you get exactly this thing up here. The C2's cancel up here, 2's cancel, and so on. So this is actually the inverse. So now we're almost done with this nice simple example. And you get this matrix times this matrix. Oh, sorry, step backward. Times that matrix up there, 2B1, negative 2B2. These are B's and X's, but whatever. And that gives you this one right here, which is the matrix. So I'm going to fit it here. B1 over C1 up there, and then so minus that's 0. These are zeros, by the way. Should have zeros here. And this one gives you 0, and this one is B2 over C2. So what it says is that, assuming the B's are positive, that if you so that the where is it? So the first, how do I say this properly? The first. So remember what the Jacobian is. The first row is the derivative of here B star, I guess, 1 with respect to C1 and C2. What this tells you is B1 is not affected at all by C2 in this case, and it's affected by C1 in this fashion. Oh, I put the negative up front, that's the problem. Negative. Assuming C and B are positive, it's decreasing in C1, as you might expect. And the same deal with B2. It is also decreasing in C2. So again, pretty simple. It's the example in the book makes more sense in the sense that it requires you to use the implicit function theorem to derive this, but I cannot fit the example in the book on the screen, and flipping back and forth between 5 screens would be very confusing. So go check out the book for this example. I apologize for not making a more complex example here, but I think you see the point, how this works. I'm going to go through it one more time. You have some utility functions, one for each player. You take the first order condition for each player, set it equal to 0. These, your optimum b's here, are implicitly defined by these first order conditions. You then compute the Jacobians related to both the parameters c and also the, it should be b's instead of x's, but also the variables, the choice variables, the b's. You invert the matrix for the Jacobian corresponding to the b's, or the x's, or whatever. You multiply that inverse matrix times the matrix, the Jacobian corresponding to the c, the parameters. Multiply the whole thing by -1, and that gives you the Jacobian related to the optimum. What does that mean? Well, you think back to what the Jacobian means, which is the first row of the Jacobian tells you the rate of change of the first optimum piece, the component, b1 star, with respect to both of the components, and the same thing with the second one, with the second row for the second component of b2 star. So you can read off from the Jacobian matrix how each component of your optimum, each component of your b star, b1 star and b2 star, change in equilibrium with changes in c1 and c2. So in those 4 elements of this 2x2 matrix, you get how each of the 2 components of the optimum b star change with each of the 2 components of the parameter c. And that is it. In the book, you have off-diagonal terms because now, since their chance of victory is an arbitrary function of b1 and b2, they could be multiplied together, in which case you end up with b2s in g1 and b1s in g2, and you get the situation we talked about before, in which you have this chain of affect and effectiveness, or affecting each other, whatever. And then you get off-diagonal terms indicating that c2 will affect b1 indirectly because c2 affects x2, which affects x1. So you can trace out the entire chain of logic via looking at the components of the Jacobian that you get by using the implicit function theorem, and I recommend that you go through and take a look at the book example and see that because there's a little more space there to write that stuff out. Okay, well that is it. That's the end of this module and the end of this lecture, the end of this part of the course. I hope you've enjoyed it and got something out of it, and I thank you very much for watching.